So I have this box here. What is inside? There's a plate inside, right? Can everyone see the plate? Okay, very good. Now, I have this stick. And if I'm careful enough, I can just put this stick right through that plate till the other end of the box and remove the stick. So what is inside? What can be inside? How can this happen? Like, I just drive this stick through the plate, that solid plate, move it to the other side, and remove it from the box. There's no plate inside. Yeah, exactly. There is no. It's a magic plate, right? It's not magic. Actually, this thing is called physics. In fact, it is called optics. Okay, so it has to do something with light. What can we do with light in order to achieve this result? Any ideas? You study physics, right? Like you have. Okay. Okay. What grade are you in? 13th. Oh, 13th. Okay. So, what can be inside of this box? I'll show you. Oops. It's a good idea. Maybe there is a mirror inside, but if there was a mirror, I just couldn't stick the.
A magic mirror.
Oh, it's a magic mirror. Very good. Actually, there is nothing inside. Okay, you can see there is nothing here. I'll show you how this phenomena can be achieved. Have you all been to 3D movies, 3D cinemas? You probably know this, these pair of glasses, right? Okay, it's not how we achieve this effect. It is achieved by another type of glasses that use two polarizers, okay? Well, oh, actually I prepared with some extra light source for you. Have you learned about polarizers? Yes. Yeah, okay. So that's how you have the glasses on you, right? If you just break them and move them on top of each other, no light can pass through, right? If you turn them 90 degrees, light can actually go through both lenses. What I have here is two polarizers, okay? I put one here and put the other one behind it. Can you see anything of the light? No, you can't, okay? But if you turn it, you see it much brighter, right? So you can see light is passing through. So, who could explain me how this box works based on this knowledge we just gained here? Any ideas? Yeah, there are polarizers. Two on this side, two on the other side. And these are caught here, right in the middle. Can you see it? These are arranged in a way that they would block out light coming from one direction. So it would look like a plate is there inside. So one polarizer stands like this, the other one stands like this, okay? 90-degree angle, they are perpendicular to each other. The other way, the other side works exactly the same way, only in the opposite directions, okay? So wherever we cannot see the light passing through, our brain tells us that it would be impossible to see nothing. That's why our brain keeps convincing us that there must be a plate inside. But we look inside, we know there is nothing there, so we have to think how this can happen. It's so simple. But if we have polarizers now, let's do some tricks with it, okay? One trick with polarizers, what engineers do is they put transparent plastic things in between. Have you tried this? Ever? What happens if you put something transparent in light? Okay, in polarized light. Can you see any difference? No, you can't. Should I talk about polarization, or you know the principles, right? You know what polarized light is? You know what waves are, electromagnetic waves? Light moves in all sorts of directions. What polarizers do, they just direct the light. Can you see something now? What happened? What? Wow, yeah, it's really wow. In fact, if I turn it, maybe you can see it much better. You can see this transparent plastic in between two polarizers became rainbow color, right? So you can see the rainbow here. In fact, the more I twist it or bend it, the more colorful it gets. I don't know whether you can see it. I try to stand it here. Maybe I build some structure here that can hold it together. Okay, this way. So when I put these transparent objects in between two polarizers, they just change the color, which you cannot really see here. Anyway, I try something else. Okay. If you have a transparent tape, okay, transparent plastic tape here, you put them on in different layers. They will just alter this polarized light in different ways, okay? The thicker it gets, it lets more and more wavelength through, or it alters the wavelength that can just go through. And one more thing you can look at here. What happens? What happens when I'm rotating it? It changes the color, exactly. So now I have a glass pane here. I just put plastic tapes randomly in many, many directions. So I put this in between. It looks really cool, actually. So let's see what happens if I put the second polarizer here. You can see the colors. Now just pick any objects you want here, okay? Just get one object. Can you see it? What happens to it when I change this polarizer? It changes the color, right? But how it changes the color is what really matters. Just look at this yellow triangle there. Can you see the triangle, the yellow one? What color will it become when I rotate this? Red? Blue? Who says red? Raise your hands. No. Okay. Who says blue? Well, it's sort of blue, yes. It's the complementary color of the yellow that appeared here. It is because one time we excluded some wavelength, and when we rotated it, we blocked the only wavelength that passed through for the first time and let all the other ones go through. That's why we get the complementary color here. What I personally made is my favorite trick here. It's just a piece of glass. Do you know this? Yeah. Ah, okay, good. I'm happy. Okay, so talking about light, let's do some other trick with light. I knew I would come here, so I brought something which you might not know what this is. It's transparent. It's transparent nail polish, okay? I know not too many girls are in this school, that's why I just told this. We will make a little trick here. It's sort of nanotechnology we will just produce. Actually, I brought many, many pieces of paper for you, so anyone can do it after me, or we can just set a table behind, whatever. So we need You need some water. Maybe you can come a bit closer because you will see it that way. Okay. We have water. I put a piece of cardboard in the bottom of this bowl here. Okay. Could you hold it down for me? Just one corner. Okay. Now I use the nail polish. And just put one droplet over the surface of the water. Whoever is close enough can see something over the top of the water. What happens there? Yeah, it's pretty much like oil spill over a puddle. The only difference is it really behaves like the oil spill you can see on the surface of the water. The only difference here that it will remain because of all the chemical agents in this nail polish. So when you let it go, it comes to the surface. And if we are good enough, we can just lift it out. And if you dry it, okay, it's a bit yucky, but when you dry it, you can have a portable rainbow, okay? You can bring it anywhere. If you want to see a rainbow, you just get it out of your pocket and you can look at it. You can keep it. If you want to make some, I have cardboards and I have the nail polish so you can play with it. Maybe after the presentation. So what happens here? So when you put the droplet of nail polish on the surface of the water, it spreads evenly on the surface, okay? And as it spreads, it forms a very, very thin layer. This layer is only a few hundred nanometers wide, okay? It's very, very thin. It is so thin that it's comparable with the wavelength of the light, okay? You have this layer here. You have an upper layer, okay? An upper surface and a lower surface of the layer. So when light comes in, it passes through the top layer. Some parts of it bounces back, of course. And another part of that ray just comes to the bottom, okay, and reflects from there. And when these two lights, maybe I would need, okay, this is the film we have here, okay, that thin layer. So parts of the light bounces back from the surface. Some parts of the light reflects from the bottom, okay? When this reflected light beam meets this reflected light beam, they will interact with each other, okay? So what we see here is called rainbow. Yeah, rainbow is what we see. What happens when we add two waves together? Actually, I'm thinking of the word myself as well. But interference, yeah, interference, okay? So that's how you can make light interference at home. And it's very simple, and it looks good. Kids usually love it. You're not kids anymore, I'm afraid. Okay, whatever. That's all about light. Now let's talk a bit about electricity, what I also bought. You know this device? What is it called? It's called Wimshurst generator. What you can do with it, just build up charges in these two columns here. These are called Leyden bottles, okay, or capacitors. These are very primitive forms of capacitor. I don't think I have to talk about capacitors in this school, so you must know it. Whenever we build up enough charge, you see a little spark over there. What can be the voltage of this spark? 3,000. Who says more?
5,000.
Yeah, it can be. It is quite possible. Like dry air has about 20 kilovolts of whatever. Átütési szilárdság. Okay. So if I put these two balls in 1 centimeters from each other, we get about 20,000 volts. If this distance is higher, it's more voltage, okay? Who dares to touch it? Come here. Okay, now this is come here to this side so others can see your facial expression. Okay. You don't have a pacemaker, right?
No.
Hearing aid?
Not yet.
Okay. Not yet. Good. So it's about 3 centimeters. When I say no, just put your finger in between, okay? Leave it there.
Oh, yeah.
What did it feel?
Cool.
Who else wants to try it? Okay, I think all of you should try it. So now, a little interactive demonstration. Everyone stand up. Form a circle. Just make a big circle. It doesn't have to be symmetric or... Okay, does any of you have pacemaker? Senkinek nincs szívritmus szabályzója, ugye? Hallókészülék bárkinél? Jó. Now, hold your hands. Hold the hands of the guy standing next to you. Okay, everyone is holding hands with the one next to him? Good. From now on, you have to be very careful. You have to pay attention to only 2 things. 1, don't release the hand of the guy standing next to you, okay? Number 2, don't touch me. Hold this. Matt. You may be seated now. We have very low current here, okay? Never try it with the wall socket, okay? Never try to do that. And also the electric impulse we have here lasts only for a very, very short time. That's why nothing really happens here. If we had much higher voltage, yes, it could do some damage, but such a low voltage of somewhat 100,000 volts is nothing, so we can play with it. But now, I want to try something with you which succeeds very rarely, but if it works, it's really very, very good. So, first of all, let's do a little introduction to it. I have a professional device here. Who can tell me what this is? Igen, valóban olyan. So, conductor? Yeah, these are conductive materials. Yeah, these are capacitors, okay? So we can build up a lot of charge on these 2 plates of the capacitors. Let's see if it works. Okay, I'm testing it now, so maybe it won't work for the first time. How can we know our capacitor is charged? Lick it or what? Yeah, touch it. Yeah, I could touch it, that's one option. Or I can just use a ping pong ball, okay? I put some aluminum foil over the ball. It's very light, okay? And if I put it in between the 2, nothing happens. Add some more charge to it, maybe. And now it works very neatly. What happens here? Why does this ball start to move from one side to the other? Yeah, electrons have to move here. When this ball touches one side of the capacitor, it gets the same charge as that side, say negative. Okay, say this side is the negative part. The ball becomes negative. We have 2 negative objects. What will happen? They will repel each other, right? And from the other side, there is some attraction, right? This is the positive side, so that attracts the negative ball. What happens when the ball touches the positive side? Yeah, it gets positive. So the same phenomena will happen over and over again when we are carrying out this experiment. But now, I'd like to build a human capacitor, okay? I would need 2 people who are brave enough to participate in this experiment. Sometimes it works, so maybe it will work now as well. Should I just pick? Okay, you too. I just need 2 hands. Straighten your palm. Come to the other side. Hold this wire with the other hand. Good. Igen, lehet, hogy egyszerű. Okay, try to straighten your fingers if you don't want sparks in between your hands. Okay. Oké, ezt nem gondoltam, hát igen, gyertek egy kicsit közel. Okay. Kicsit közelebb a tenyerőteket. It will not work. Yeah? Thank you. Okay, let's do it again. A bit further.
Wow.
Can you see it? Okay, now you can touch your hands. Okay, thank you very much. Is there still time? Oops. Do you want one more experiment? Perhaps? Okay. This will be one of your favorite subjects, probably. It's chemistry. You like chemistry? Yeah. Okay. What is this here? So what is this? Okay, it looks like a test tube, but actually it's the pre-form of plastic bottles, okay? It's PET, it's a plastic. They inflate it on high pressure with hot air in a form, and that's how they produce these types of bottles, okay? Only this is 2.5 liter bottle. What we need for a chemistry experiment is a fizz tablet. Actually, half of it will be enough. And I would need some vegetable oil, okay? You have all tried this experiment, right? When you put a fizz tablet in water, right? Have you ever tried to put it in oil? No. Okay, good. Would you hold it? There can be 3 outcomes, right? 1, nothing will happen. 2, it would just release bubbles just as much as it does in water, right? Or number 3, well, we'll see. Lift it higher so others can see it. Are you ready? And nothing happens. Nothing happens because in order it to release carbon dioxide, it needs to meet water, right? That's when this chemical reaction occurs. That's why I asked for some water. So thank you. I don't know who brought it for me, but thank you very much. So when I pour water over the top, what will happen to the water? It will go down. It will sink to the bottom of the oil because it has a higher density. Okay. Whenever it reaches the tablet, it will start to fizz. And that's where we need this cap here. We can make a very cheap lava lamp this way. If you look closer, there are small water bubbles that rise to the surface of the oil because they are full of little carbon dioxide bubbles, okay? So they have a lower density than oil. When they come to the surface, they put out the excess carbon dioxide, they become heavier, or the density grows, and they will sink back to the bottom, okay? So that's how you can make a very cheap lava lamp imitation at home. The only drawback of this experiment, or it seems to be a drawback, is after a while this will stop. This will stop because the pressure will increase inside, okay? When the pressure is too high, no carbon dioxide is formed any longer anymore because carbonic acid will form, okay? Carbonic acid, you know what that is? Okay. When we have high pressure, it favors carbonic acid formation. When we have low pressure, carbon dioxide bubbles will form. I can prove it. Now it almost stops. Only a few bubbles go to the surface, but when I release it, as pressure released, again, all the carbonic acid breaks up into water and carbon dioxide. Carbon dioxide bubbles will raise the water again, okay? So you can just play with it. Whenever you are bored, just put it in your pocket. When you want to see it again, you just release the pressure, and you can look at it again. So that's what I wanted to show you. Thank you very much for your attention. You were a great audience. And whenever you have time, just come to the Palace of Miracles, and yeah, you're welcome there as well. Thank you.